All right, so hopefully you can see and hear me, guys. Sorry, I'm not there. I'm actually in Spain, in Europe, for a conference called Mobicom. We need to present something this week, and unfortunately, my student couldn't go, so I'm going on his behalf, on her behalf, actually. Um, so yeah, we're gonna do this today like this. Again, apologies. But as Justin said, there are multiple ways you can ask questions. Either just raise your hand traditionally and ask your question, and Justin will either type it in or just repeat the question for me. Or you can join the meeting ID and just type your question or just unmute yourself and ask a question right away. Okay. Um, is there anybody has any questions before we get started? We're good? All right. So today I want to talk about ISAs, okay? Just a couple of kind of things to mention that, PTEs is still being processed. I actually like a few spots opened up by the department. I wasn't aware, unfortunately. But I think most of the people on waitlists the last time I checked got in. But I'm gonna just follow up with them um, uh, after the class, post something on Campus Wire. You can always email me. Okay. So that's for the PTEs, but let's continue. All right, so last time we talked about kind of this figure, right? So we talked about various different stages of computer architecture and generally computing systems. We said that essentially kind of like, general purpose computers started kind of in 70s. And since then, we managed to actually significantly improve our, computing performance, right? So we started from, if this was like the baseline performance, right now we are around 50,000 times faster computers. And I also said that this is not just faster, it's lower power, much smaller, and very importantly, it's very, very low cost, so much cheaper. So it's a significant improvement in terms of various different things. We said that generally there were two main reasons for this. One was the technology that we use, better CMOS technology. We talked about Dennard scaling, and we talked about Moore's law, which is the important, rule that kind of drive the semiconductor business since the 70s and early on. But we also talked about this kind of different regions. As you see, there are kind of different numbers here, and I kind of describe the reasoning behind these numbers. And this is kind of like what we're going to do during this class, okay? Like we're going to talk about all these things, starting all the way from like golden age of computer architecture, which we managed to have 52% per year improvement until now, we kind of stop, but we are doing other things, okay? So this is kind of like, what we did discuss last time. The last thing that I said was, is this the end of it? And I said just to know there are actually new technology and techniques that we are using these days. There's more than more, and beyond CMOS, which I'm going to talk about later in the class at the end of, lectures, actually in week 10, when I'm gonna basically just briefly talk about GPUs and other chiplet systems and so on and so forth. But this is kind of the story of a more advanced course if you want to if you're interested to learn more about these. Okay. So now let's jump into a new topic today, and that's the instruction set architecture, or ISA. If you remember last time, I kind of like discussed why we need an ISA. We have a bunch of different applications. We have the system software, and then we have the hardware, underlying hardware. And the problem that we have is maintaining the compatibility between these, because we might have different applications, we might have different hardware implementations, uh, and because of this, we need to kind of figure out a way that how a software developer can develop software without being worried that what sort of hardware would be underneath, okay? And we explained the concept of instruction set ISA, which is basically kind of this contract between the software, hardware, and kind of enforced by the system software. Essentially, as I said, ISA is this contract between the software and hardware. Typically, it's described by giving the programmable visible state. And as I said, for the software side, This states is basically the registers and the memory, and then semantics of the instructions, essentially like the sequence of instructions. That's what the software developer or the software in general needs to know. IBM actually was the first kind of company that's kind of bring the idea of ISAs, and IBM 360 is actually was the first one to kind of say, okay, microarchitecture could be different than the ISA, so they kind of standardized this. But one thing to know is that there are many, many different ways of implementing a given ISA, okay? So for example, AMD and Intel both use x86 or AMD 64 ISA, but they have very, very different implementation for that. So given one ISA, there might be different implementation for that. And that's the story that we're going to talk about next week, actually. And then another good example is ARMS ISA, which many companies, including Apple and Qualcomm and Samsung, is using it, but they have very different implementation for that. And they also have what we call custom instructions, which they add actually more instructions to it. Anyway, what we're going to use and what we're going to focus in this course would be RISC-V ISA. RISC-V is actually now a big organization. If you're interested to know more about it, if you go to risc-v.org, you'll see more things about it, okay? So before jumping into the details of ISA and particularly RISC-V ISA, which is the focus of this lecture, I want to also give you kind of an overview of what it's like to have different ISAs. So typically, as I said, ISA is different than the microarchitectural stuff, the microarchitecture that we're going to implement that particular ISA. But typically, for a given ISA, there is a typical methodology that we use to implement it. What we are focusing in this course is a RISC, a reduced size instruction format. But there's other things such as a CISC or VLIW or virtual machines and so on and so forth. And typically for these different kind of like ISAs, there's a different type of implementation. What we are interested in is RISC, so we're going to focus on what we call hardwired and pipeline structure. I'm going to talk about those things next week, so you're going to understand that. But before kind of going very focused on that, I wanted to kind of show you that there are other implementations. We're not going to have time to go over them, but just know that they exist, and sometime in future you might need to know them. Okay, and then this is also not kind of like a requirement. You can have, for example, a RISC ISA, but have a pipeline structure. This is basically many of Intel processors that they're doing. You can have like a Java virtual machine based on RISC and so on and so forth. But anyway, we're going to focus on RISC, and we're going to focus on what we call the hardwired pipeline machine. And I'm going to explain all of these things to you. Okay. So what is RISC-V? RISC-V is basically this what we call an open source RISC architecture. In the next slide, I'm gonna show you what is RISC. But RISC-V is essentially what we call royalty-free, which means that if you manage to kind of design a particular microarchitecture and implement it using RISC-V, you don't need to pay any royalty fee to any company, versus if you use other ISAs, including ARM or x86, that's a different story. It's mainly maintained by the open source community, so it's actually mostly academics and different industries. And what we're going to focus in this course is what we call the base mode, which usually shown as RV32I. The 32 part is basically the size of the instruction, as I'm going to explain in the next few slides. There's also a 64-bit version, there's a 16 version, and recently there has been a 128-bit version. So we're going to focus on the 32-bit version and the base version, okay? And again, I'm going to show you what difference does this make, okay? All right, so what is RISC? So RISC stands for Reduced Instruction Set Computers, okay? In order to understand what is RISC, you also need to understand what is CISC. The difference between RISC and CISC is basically the complex version of that. So it's complex instruction set computers, versus RISC is reduced instruction set computers. The difference between them is risk is like tries to be very simplified and simple. Okay, so every instruction has exact same size. For example, if you're saying that we are working on 32-bit version of risk, it means that all the instructions that we have, they have exactly 32 bits. Okay, so this is 32 bits. Okay, and then another thing that Rust has is that they typically every instruction just does one thing. Okay, for example, just adding, just multiplying, just XORing, storing, loading, things like that. Versus the CISC architecture, style is about doing complex things. Okay, so we add and modify, for example, add and multiply together, and so on and so forth. There are a few exceptions, especially for ARM ISA, that there are complex things that have been done with the same kind of operation. But typically in this course, we're going to focus on instructions that are very simple and the same size. So all of them are 32-bit, and each one just do one particular operation. Okay. So it's kind of like simple one by one. And RISC generally is more popular than CISC. The only CISC, instruction set that's still widely used is x86, which is used by Intel and AMD processors. But all the mobile and lower end systems, everything that's based on ARM is essentially RISC. And then given that RISC-V is also getting lots of traction these days, RISC is going to be more and more popular. If you want to kind of see more details about the difference between these two, this is a very useful link that kind of like go through the difference between RISC and CISC. We're not going to talk about CISC architectures here in this class. We're going to mainly just focus on RISC. So that's also one thing to note, okay? I think some of you in CS33 probably talked about and have seen something on x86 and the CISC, but as I said, from now on, we're going to only focus on the RISC architecture, okay? So widely used, ISAs, as I said, all of them are RISC except x86. So the other popular RISC ISAs is MIPS, which was very popular back in the day, but these recently is not being used that much. ARM, of course, that probably all of you have heard about. And then ARM variants are, for example, the Mac, Apple's particular implementation of ARM. In all this, their custom silicon like M1 and M2, they are all ARM-based processors. All of the IBM's systems, PowerPC is also RISC, and of course RISC-V that we're going to focus in this course. All right, so now let's kind of focus on kind of design methodologies for RISC-V, why we are making these decisions, and so on and so forth. So I'm going to basically break down the kind of the instruction format in RISC-V. We're going to talk about different instructions. But before kind of going into the details of, okay, this is one command and this is another command, let's actually think about how do we actually run these instructions on computers, because that will help us to kind of take a step back and then think about, okay, how should we design an ISA? Is there any questions so far before you jump in, Justin? I don't see anything in the chat, but let's see if there's anything in the class. We good? I guess we are. Okay. So let's continue. Are we good, Justin? Thumbs up?
Yeah, we're good.
Okay. Yeah, sorry. All right. So the way that we run instructions in our computers is based on this type or format called stored program computers, or in other words, it's what we call a von Neumann machine or von Neumann computer. So what is that? So essentially the idea of a stored program computer is that think about computer hardware as this machine that reads instruction one by one and execute them one by one sequentially. So in the same program order, we just go through the instructions and run them one by one, okay? And we kind of continue this until the program finishes. How do we load this program? How do we start this program? And when do we know that the program is finishes? There are different stories. And then we're gonna break it down. So kind of what is this sequentially, what is this one by one, and what finish means. Part of it is kind of the operating system job, which we're not going to talk about, but most of them we're going to cover in this class. But what I want to show you in this slide is essentially think about hardware as this machine that kind of, if this is your instructions and these are like, list of one by one, think about this, each row is just one instruction. Essentially what the hardware does is kind of take this instruction, execute this, go to the next instruction, execute this, and next instruction, execute this, and so on and so forth. We call this a von Neumann machine. Alternative to this is like data flow kind of schemes or VLIW schemes that we're not going to cover. And because von Neumann machines is the most popular, the most dominant type of computers. Almost all the computers that you have and use is a von Neumann machine. That's why we are focusing on this in this course. All right. So to give you a little bit more detail of a store program, essentially there are kind of two things that we need to have in hardware. We need to have memory, and we need to have kind of what we call the CPU or the processor. What happens is your instruction and data both goes into your memory. So your memory is basically the combination of instructions and combination of data, okay? So both of them are stored in the same memory, same format, okay? So there is, and from the memory point of view, there's no difference between what is an instruction or what is just your raw data, okay? And we typically just save this in a continuous regions of the memory in a linear array. Think about memory as this giant array that you can actually index it one by one, okay? And then what happens is that the CPU basically has this special register called program counter. So inside the CPU, we have this thing called PC or program counter, which is a register. What this PC does is basically knowing where the first instruction is, okay? So think about this as, again, the giant index or memory, the giant array example. If your memory is basically an array, you basically index it with like X, and then you read a particular part of your memory, okay? So what does this PC does is basically PC is pointing to the beginning of whatever program that you want to run, okay? Beginning of your program, which is, let's say, for example, is address 100 or whatever. I'm just making up numbers, okay? So particular address. And all it does is basically just go inside that address, bring the first instruction to the CPU, execute this instruction, and then goes to the next instruction and brings that one and then execute that one and so on and so forth. Okay, so this is kind of like the idea of how we execute things. Okay, so we use a program counter to know where the beginning of our program is. We're going to fetch that instruction from the memory. Basically, fetching means just reading it from that particular address. We're going to then execute this instruction. And as I'm going to show you in the next lecture, this execution means just updating the states of various different things. And eventually we're going to update our PC because now we need to go and execute the next instruction. Okay, so we're going to add PC to the next PC, whatever that is, and then go and fetch that and repeat the same process over and over again. Okay, we're going to continue doing this until we finish the program. Excuse me. So this is kind of like the idea of a slow program order. If we manage to kind of translate our software into a sequence of instructions, then we load these instructions into our memory, and then we're going to use this kind of format to execute them. Okay, so this is kind of the idea that we have. For now, we're going to focus on kind of this part and how we actually kind of translate things from software to the instruction. Later, we're going to kind of focus on this side of this system. Okay. So let's focus now on how to build an ISA. So what are the things that we need to know about? We're going to go through the details and so on and so forth. Essentially, the biggest thing from ISA is we are translating a high-level language, a C, or Python, or something like that, into what we call an assembly, right? I think most of you are already familiar with what assembly is. What assembly is essentially this format of of writing instructions with the registers and so on. We're going to actually break it down how the assembly of a RISC-V would look like in this lecture. So the rest of this lecture is basically about that. We're not going to, for now, discuss how to generate the machine code, which is essentially the step after generating this assembly. We're not going to talk about how to upload this into hardware, and we're not going to talk about how the hardware actually going to run this for now, okay? For now, we're going to just mainly focus on kind of this transition, all right? So how does the RISC-V instruction and generally any instruction looks like? If I want to give you a kind of a high-level picture of any instruction, especially a RISC instruction, each instruction kind of has two main parts. It has a command part and it has an operand part. So the command part is basically saying what we should do. By V, I mean the CPU. So the command tells what should be done. For example, adding, multiplying, subtracting, loading, storing, all those things, right? So this is the command part. And the operand, of course, is the data that we are using. So, you know, for example, if it's a load from where? What is the address? And then the other important thing is what is the destination? What we're going to do with this operation? Once we do this operation, what we're going to do? Are we going to store it somewhere? Are we going to update some registers and so on and so forth? Okay, so these are the two things that any instruction has in RISC-V. So let's break these down. So let's see how many operands, what type of operands do we have, and then let's also break down how many commands do we have. So let's see if we can have and if we can finish this in this lecture. An important thing to remember is that we're focusing on 32-bit RISC-V ISA, okay? Which means that every instruction is basically 32-bit wide, okay? So everything is 32-bit wide, and all of them are fixed size, are exactly 32-bit, right? So everything 32 bits, combination of commands and operands, all right? So let's now focus on the operands. So let's see what type of operands do we have, and what are they? So essentially on RISC-V, you can have three types of operands. You can have registers, you can have immediates, and you can have memories, all right? Registers essentially is this kind of storage units inside the processor, okay? The difference between register and generally a memory is that registers are very, very small, but they're very, very fast. So you usually can kind of access registers in nanosecond, delay time, okay? Which means that you can access these things in one clock cycle. I'm going to talk about why one clock cycle is important for us later when we talk about pipelining. But essentially, the idea of register is that if we have my CPU here, and if I have my memory here, okay, I have all the storage here, right? So this is basically the primary use case of memory storage. But accessing memory is usually very slow, okay? So this access, unfortunately, is not as quick as we want. So what we do is that we kind of have like a smaller storage area here, and we call this register, okay? A set of registers which we call register file. So these registers are inside the CPU, but since we don't have enough space, we cannot really have a big set of registers. So the registers are small, but they're really, really fast, okay? Later on, when we are talking about memory hierarchy, you will see that's why this is important, why we're going to use this. But for now, just consider that registers are this kind of temporary thing for us to store things very, very quickly, okay? So essentially, remember this, and we're going to come back to this many, many times in this course, and that is essentially faster memory is unfortunately small, okay? So the smaller, the faster. So registers is the fastest thing that you can access in your system. If you go with the giant hard drive, which has terabytes of data, that's the slowest, okay? So it's usually the other way around, the way it works. Important thing about registers is that registers they can be seen by software. If you remember, I told you that at the software side, what we see is registers and generally all the memory. So the software sees all the memory, including the register. At some point in future in this course, we're going to talk about some registers that the software will not see, and we're going to explain why this is an important thing. But for now, when we're saying register, it means that you can actually access this register at the software level, at the assembly or at the high level language if you want to. Okay, we typically have somewhere between 16 to 64 registers in modern ISA. Okay, that's how small it is. We don't have many registers. We only have very small set of registers. Okay. And then another thing to remember is that we can have larger registers. Okay, since we are kind of dealing with 32-bit architecture, our registers are 32-bit wide. Okay. So any register that we have in this RISC-V 32-bit version are 32-bit, okay? But nothing prevents you of having, for example, a 64-bit register, okay? So why are we not using, for example, a 64-bit register, or why we are not using a 16-bit register and so on, is that essentially the size of the register is a trade-off, okay? The larger the register is, of course, you have more opportunity to data transfer, you can have better performance and so on. But larger register means that you need to transfer more data, which means that you're consuming more power, okay? So essentially what happens is that in high-end processors, in like cloud computers and like servers and so on, we have like, very wide registers, usually 64-bit or sometimes 128-bit registers. But in low-end systems, in mobile devices, battery power devices, and so on, we typically tend to have like very small size registers, 32 or even 60, okay? So that's just kind of like the difference between a 32-bit version of a particular implementation versus 64-bit. As I said, we're gonna focus on 32-bit for this course, but the principles are the same when we're talking about 64-bit as well. And the reason that we have 32 versus 64, again, is for the power and performance reasons. 64 give us more performance, but also gives us, unfortunately, more power. So we need to kind of adjust as a designer. All right. So this is kind of just reiterating what I just said. So in RISC-V, we have 32 registers. Each one is also 32-bit. So 32-bit registers and 32 of them, okay? In terminology we use in RISC-V is 32-bit called word, okay? So if you have 64 bits, it's called double word, all right? So this is what we call RV32, RISC-V 32-bit version, okay? When we are saying that we are implementing RISC-V 32, it means that we're gonna have 32 registers, each one is 32 bits, okay? And as I just said, there is also a popular other implementation of RISC-V, and that's RV64. The difference between 32 version and 64-bit version is that in 64, we still have 32 registers, but each one is 64-bit wide, okay? They're wider, they're faster. And 64-bit, we call it double word, okay? So word is 32, 64 is double word. If you say half word, it's basically 16 bits, okay? All right, so let's continue. So in terminology of assembly in RISC-V, each register is shown by X, okay? So X0, X1, X2, and so on and so forth, okay? We have 32 of these, so the numbers start from X0, go all the way to X31, okay? An important thing to remember is in RISC-V architecture, X0 is always 0, okay? Which means that it's hardwired, literally hardwired into the ground. So if you actually try to write something to X0, nothing will happen, all right? So things will be ignored. The reason that we are using 0 and X0 is because there are lots of scenarios that we need 0 in our systems. Actually, when you start writing your programs, you will see that, 0 is very handy. So that's why we use X0 for this. So remember, you cannot write things to X0. I mean, there is no error if you actually use X0 as your destination, but nothing will happen, okay? So we store these registers into this data structure called register file, okay? So think about this as, again, as an array of X's, which essentially each one, so we have a 2D array that each one is 32 bits, and we have 32 of these. So this is x0, this is x1, this is x2, and so on. And this data structure is called register file, okay? Is a file of registers. All right. Any questions so far?
There might be feedback there. Nodders. I might. So basically, like in x86,
Yeah, that's what. Yeah, go ahead.
there's backwards compatibility with say like smaller register sizes. But with RISC-V, if it's static, I guess how does that work?
So backward compatibility means that you still can, so in RISC-V, you can still use a 32-bit version of your binaries, okay? And it's still, you know, supported by 64. You cannot use a 64-bit version of your binary and run it on the 32-bit machine. This is the same story for even x86 and Intel machines as well. That is, we are not really running, we cannot run things that are 64-bit version on 32-bit version machine, but you can do the other way around. The same story for RISC-V as well, okay? So if you have a 32-bit version of a binary, you can run it on your 64-bit machine, okay? Any other questions? You can also use the chat if you want to.
So the follow-up question is, in RISC-V, is the limitation that you have to use a 32-bit register file size? Is that fixed?
I think the question is there limitations on using only 32 registers and not more? Because you can either use 32-bit version or 64-bit version, and as I said, there's also a 16-bit version. But the limitation, the hard limitation is you can only use 32 registers. You cannot use like 48 or 64. The x0 to x31 is hardwired. There's no, you cannot change that, okay? We're gonna use another trick in order to expand the number of registers later when we are discussing the difference between architectural registers and program registers. But for now, just think that we only have 32 registers. They are either 32-bit wide or 64-bit wide, but you cannot add more registers to the system, okay?
That answers your question. Are there any other questions? Yeah. 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 Does the 16-bit version of RISC-V also have 32 registers?
Yes. 64-bit version is a little bit different because it's a compressed version. So there are various different implementation for it, and it's not been standardized yet. But yes, it usually has, again, the 32-bit registers. Sorry, 32 registers, each one 16-bit. I'm also confused.
Oh, wait, one more question? Why is x0 hardwired to 0?
Why x0 is hardwired to 0 is because of reasons that we want to have zeros at the beginning, okay? So there are things that we later on we're going to use x0 as kind of our baseline, and we want to have a clean 0. Again, in your homework actually this week, you're going to use x0. You're going to see how x0 is so handy and how it's useful. It's a design decision that's initially, I mean, we can live with not having x0 hardwired to 0, and many other implementation doesn't have that. But generally, x0 is because of many use cases that you're going to see later on in this class.
Also, if there's any more questions, you can also like raise your hand and I can field it to Nodder. Do you want to keep going, or we have one more question here if you want to answer that?
Yes, let's finish it and then let's continue.
Okay. Oh, we're continuing, or we're asking the question?
We are answering questions.
Okay, yeah, what's your question? Is Linux dev slash lol linked to this X0 register or not?
Say it again. Is Linux what?
It was like Linux dev. He was wondering about Linux slash dev slash null, and if there's any connection to the X0 register.
It's a particular implementation of operating system is not necessarily using this, but most cases, if you want to have a 0, you will use some form of X0. Yes. That particular implementation might be different from one particular kernel to another, but typically, if you want to use 0, you will use X0. Okay, so let's continue, but we can definitely answer more questions later. Another thing that I want you to remember is that all these 32 registers that I talked about, they are all use integers, okay? So we're not dealing with floating points or anything like that. So all these 32-bit registers are storing integers. For high-end processors that you need floating point operations, there is a separate set of registers, which we call floating point registers. So there is a separate register file for floating point and a set of different registers. We usually show them as F, okay, F0, F1, and so on and so forth, which is different than X0, X1, and so on and so forth, okay? For this class, we're not going to talk about floating point registers and generally floating point operations. We're going to focus on base implementation of RISC-V, which is just integer operations, okay? All right, so that's it with the register. Essentially, if you want to access operands in your instruction, you're going to use something like this, X1, X2, X3, and so on and so forth, okay? And also, pay attention to the methodology, the syntax that I'm using. So I'm using X and then a number. I'm not putting this into any parentheses or anything, okay? Just X and the number, okay? That's how the compiler understands this. So now let's focus on the second thing, which is the immediates, all right? So what are immediates? Immediates are just constant numbers. There are many, many scenarios that you want constant numbers, okay? Like 0, 5, 6, 7, 8. And these constant numbers could be signed, so it could be negative or could be positive. Again, they are all integers, but they could be negative numbers or they could be positive numbers. How many numbers on what sides of integers can we show? Depends on how many bits do we have for the immediates. I'm going to show you later how many bits we have for showing immediates. But think about it, somewhere between like 8 to 12 bits. This is like the most you can show. So numbers between -1000 to +1000 is kind of the range that you have for immediates, okay? So to give you one example, this is your first RISC-V instruction. So essentially what this does is calling add I, and then X2, X1, and 5. I'm going to actually break down this kind of formatting when I'm talking about the commands. But for now, just remember that this mainly says add. And this I next to add is basically, it's because there is an immediate involved in this operation. So what it does basically functionality-wise, it means that X2 is equal to X1 plus 5, okay? If, for example, I had add I, X2, X1, and -5, this would be basically X2 is equal to X1 minus 5, okay? Essentially, this immediate is kind of like, just the constant we are adding to our register X1. For now, don't worry about why this is on the left side and why this is on the right side. I still haven't discussed this command part of things. For now, just know that these are the operands. This is the register operand that I just talked about, and this is the constant or immediate that we are using. And these are also very, very handy. And also another thing to remember, this is an integer, and this is signed, okay? So it could be negative or it could be positive. Okay, 2 things to remember. So one big thing about immediates, and that's kind of create lots of confusion for people and, make a lot of discomfort at the beginning of this class, is that immediates are not necessarily 32 bits. The reason for they're not 32-bit is we don't have enough space to store a 32-bit immediate in our instructions, because we kind of hard code this number into our instruction. And once I'm showing how the instruction is kind of formatted, you will see that we don't have space for a 32-bit immediate. So as a result, in all the cases, immediates are less than 32-bit. Okay, so they're typically like either 10-bit or 12-bit or something like that. Okay, so why this is important and why does this matter? It matters because think about the scenario like this, that we are adding x1 with 5. Okay, this is a register, so this is 32-bit. And for now, let's consider that this is only 10-bit. Okay, so now we have this problem of we want to add a 32-bit number to a 10-bit number. Okay, and now that's where your M16/M51 kind of education comes into the play, which I guess most of you don't remember how this works. But the idea here is that we need to do what we call sign extension. Okay, we basically the high level idea is that we make this a 32-bit number with some format, and then we add this 32 number with this 32 number. Okay, and that's how we're going to do this addition. All right, so we're going to have this thing called sign extension, which I'm assuming that you guys have covered and know about it before. If you don't know, don't worry, you can probably go back and read the book, or you can look at the notes, or just saying another TAs will nicely gonna give you some examples in this week discussion sessions on sign extensions. In my past experience, people are a little bit rusty about like how the sign extension works. So we're gonna give you a little bit of examples this week to kind of like make you more comfortable with sign extensions. Okay, so but what I wanted to say is that the reason that we have sign extension is that the immediates are not 32-bit. The reason that they are not 32-bit is going to be described later in this lecture. But since we want to add a two, we can only do operations on same size things. Okay, you cannot like add or subtract or XOR or whatever of a big number with a small number. They have to be the same size. As a result, you have to first sign extend the smaller number, which in this case is the immediate, and then do the operation normally. Okay, between registers, we don't have this problem. So we don't have problem between, for example, X1 and X2 because both of them are 32 bits. Okay. And then the last thing is, not necessarily you always need sign extensions. Okay, most of the operation in RISC-V are signed, so you need sign extension because the way that we are showing, numbers are based on, signs bits. But sometimes you just need padding, which means that I just add zeros. Okay, so the difference between sign extension and padding is that, padding is just you're adding zeros, versus sign extension is that you are adding 0 plus sometimes ones, depending on what sort of numbers do you have. Okay, if you're very confused about sign extension, you don't remember sign extension and padding, now it's a good time to kind of, after this lecture, go back and review your two's complement and the way that you show numbers in sign version, in binary, and so on and so forth. And as I said, the TAs will give you some examples in the discussion sessions as well. All right, any questions before we jump into the memory? Are we good, Justin?
We're good. We're good. Yeah.
Okay. So the last one is memory. So remember, we are talking still about operands. We haven't got into the command part. So the third thing that we're going to have as an operand is the memory itself. Okay. Remember that we have the CPU and the memory, and we store a lot of things in this memory. And we have a small storage area in this register, but this register is not enough for storing all the things you want. At some point, you need to go and access things from your memory, okay? So memory could be one of your operands, okay? An important thing about memory is that memory should be byte addressable. The reason for this is for compatibility issues that we always wanted to have a byte addressable memory. So which means that in our memory, always each row is just 1 byte, okay? So this is 8-bit, this is 8-bit, this is 8-bit, and so on and so forth, okay? Every row in memory is just 1 byte, and we should be able to access each byte individually, okay? That's the idea of memory, okay? There are lots of things that you need to know about memories, okay? So first of all, there are two operations that we use for reading and writing to the memory. There's load and there's store. The difference between load and store is that load is when you're reading something from memory. So if you have CPU here and memory here, if I do load something, it means that I'm going and bringing that something from the memory to the processor, okay? Loading is the operation of reading from memory. Storing is the opposite, okay? So storing means that I'm writing something to the memory. So I have this whatever number here, I'm writing it into the memory. Okay, so essentially I'm overwriting whatever it's been stored into that memory line before, and I'm updating it with the new value that I'm providing, right? Because you need both of these. Both of these are incredibly important in memory because you want both loading and storing things to the memory, all right? The second thing to remember is that for memory, you always need an address, okay? So if you have a memory, we need to know which line in this memory are we reading, and we call this an address, okay? Since memory is a huge, array of, megabytes or gigabytes, so millions of lines, okay? Typically, the way that we address memory is what we call base plus offset, okay, or base displacement addressing. What does this mean is that we typically address memory on some form of xi plus some offset. This xi is the value inside xi, okay? So this is the address that we're going to use to address the memory, okay? So we're not going to do, like, let's say if you want to address 1 million, I don't know, 3,455, we're not going to directly say address is equal to this because it's a huge number and typically we cannot do it in the CPU. What we do instead is if, for example, x2 is our base, and let's say x2 is stored 3,400, then all we need to do is that our offset should be, in this case, should be, was it 55 or 65? Let's say it was 55. So our offset should be 55. Essentially, the combination of my the content of my register plus the offset should be equal to the address, okay? So when I do x2 plus 300, it means that whatever content, whatever value that's stored inside the x2 will be added to this offset, and that would be my address, okay? And again, the reason for this is if you want to address big numbers, you cannot use an immediate that's very big because, again, we cannot store this. So we need to kind of use the registers. Another thing is that it's usually very, very convenient to have the base into the registers because many things are based on some base. So everything's kind of relative to that base, okay? And again, I think some of you have already background in assembly languages. Those of you who don't, you will see examples in the homework to see how this base plus offset addressing works, okay? But just remember that this is kind of the terminology that we commonly use in this class and almost all over in assembly language in other formats as well. All right. The third thing I want to talk about memory is byte addressability versus 32-bit data. This is also a source of confusion for many, many people. So what we have, as I said before, is that on memory, we store things in rows, and every row is just always 1 byte because we always want to have what we call byte addressability. I should be able to just read 1 byte, okay? So I should be able to address this, I should be able to address this, and so on and so forth, okay? So that's one thing that we want. But there's also another thing that we really want. And that is that I talked to you about 32-bit version of things, right? So we said that, for example, our registers are 32-bit, our instruction size are 32-bit, and so on and so forth. As I said, for now, we're just focusing on 32, but if you had used 64, everything would have been 64, right? So you're using everything 32, but all of a sudden, things that we are reading from memory would be just 8 bits, just 1 byte, okay? And that's not the most efficient way that we can read things and do things for memory. Added to this is the problem of accessing memory. Accessing memory is very, very slow, okay? So each access, think about it as that, think about the things that you want are books, and think about memory as garage, and then the box that you have in the garage full of books, okay? So if you want to read something from the memory, you have to go to your garage and then pick up a book and bring it back to your room, okay, in the second floor of your home. If you want to read things and you want to operate things on 32 bits and 32-bit cadence, then for reading a 32-bit value, you have to access the memory 4 times, right? Because each memory is 1 byte, and you have to do it 4 times. So again, going back to the analogy of garage and the books, you have to go to garage 4 times and bring the data that you want for just 1 register. Of course, this is kind of not making any sense, right? In terms of performance, this is a hugely, it's very, very slow. So what we do instead is that we are using this trick that whenever we are accessing memory, we're not bringing just 1 byte, we are bringing 4 bytes together, okay? So every access to the memory is always 32 bits, okay? So we usually kind of bunch them together, and whenever we are reading, so although we are reading, for example, from address 0, what we are really bringing is 0, 1, 2, and 3. So we're kind of reading them all together, and we kind of created 32-bit value. Because this is much faster, and most of the time I need all of it. So you might now ask that, what if I want just 1 byte? With this format, I'm not losing that byte addressability either, right? So I still read the 32 bits. I can ignore those that I don't want. So let's say, for example, I just want to read this one. So I still read all 32 bits, but I'm going to ignore this one, and this one. So I still can access 1 byte if I want to. But this way is much more efficient in terms of performance, because every access to the memory brings me 4 bytes together. Okay, but the addresses that we are reading, although we are saying, for example, load, let's say, this is the format that we're going to use, x0 and let's say 4, 4. This means that, this is my base, this is my offset. So go and read from address 4. We're not reading 1 byte, we are reading 4 bytes. So essentially what's going to be stored in X1 going to be address 4, 5, 6, and 7 all together. And this will be stored in X1, okay? So now the question becomes that, how do we actually combine them? Do we combine them this way? So if it's 0, this is 1, this is 2, this is 3, and this is least significant bits, and this is most significant bits. Do we store it like this, or do we store it like this? This is LSB, this is MSB. So which way are we reading things? So when I addressing X4, for example, address 4, does 4 goes to the least significant byte or goes to the most significant byte? So this is where the Indianness of our computers matters. So we have 2 options. We have little endian and we have big endian, okay? Little endian means that the lower address goes to a lower bits. So this is your little endian. Big endian is when you're the higher address goes to the least significant bit. So this is big endian, okay? Most machines using little endian, okay? Most machines use little endian because little endian is more intuitive, right? Because you expect that lower address goes lower and then so on and so forth, right? Big endian is kind of counterintuitive because you're kind of flipping things. What we're going to focus in this course is little endian, because RISC-V by default is little endian. So whenever we say we read 4 bytes, it means that address 0 goes to the lowest significant bytes, address 1 goes to the next one, then 2, and then 3. Okay, so this is kind of the format that we're going to use. All right. And then the last thing I want to talk about is alignment. Okay, so let's say, for example, that I told you that I'm going to read things 4 byte by 4 byte, all right, 32 bits by 32 bits. Okay, so if I do this in kind of like chunks of 4, so starting from 0, so I can read 0, 1, 2, and 3. Okay, all these 4 together, and boom, I'm good. If I want to do 4, 5, and 6, I'm also good, right? Because one axis gives me the entire data that I need. But think about the scenario that I'm showing here. Look at this shaded area. If I want to read 3, 4, 5, and 6, since the way that we kind of store this is kind of by 4 by 4, this has what we call an alignment issue, because essentially we're not able to kind of like, misalign this, because we want to align this in a 4-bit, 4 byte by 4 byte formats. Okay. So what will happen is that if I want to read 3, 4, 5, and 6, I need to issue 2 accesses. Okay. I'll read this first, this row first. I'm going to get 0, 1, 2, and 3. I'm going to discard 1, 0, and 2 because I don't want them. I just keep this 3. I'm going to issue another load and get 4, 5, 6, and 7. I'm going to discard this. I'm going to get 4, 5, and 3. So if I want to read a misaligned kind of 4 byte chunks, I need to issue multiple loads to the memory. An alternative to this is that if the hardware or the ISA allows misalignment, okay, if the compiler or the hardware allows misalignments, then in that case, we could have basically just issue one load, and in that case, read 3, 4, 5, and 6 together, because I told you that we can always read 4 bytes together. So if we can kind of align things the way that I wanted, I could have done just one axis and read all 4. The problem with this misalignment is that misalignment creates lots of complexity in terms of encoding and decoding data. So typically, the rule of thumb is that don't allow misalignment. And if you need misaligned data, just issue 2 multiple loads. And that's what we're going to do and focus in this course, okay? Again, by default, RISC-V doesn't allow misalignment, which means that if I want to read things that kind of sits between 2 consecutive 4s, you have to issue multiple loads in order to read them, okay? All right. Any questions so far?
Wait, let me go up to you. No, I'm gonna ask. Yeah, the question was, why can't we offset by 3 instead of 4? Does that make sense?
Because so you want to group things in 4 by 4 byte by 4 bytes format, because you want to read things in 32-bit format in your 32-bit architecture, right? And you have to start from 0, right? So if you start from 0, you have to do 0, 1, and 2, and 3 in one chunk, right? And then the next chunk would be 4, 5, 6, 7, and then so on and so forth, right? So this is how you're going to align things. If you want to read, for example, 3, 4, 5, and 6, then you're kind of like doing like this, right? So this is what we call misalignment, because 3 is from the other groups and 4 and 5 and 6 is from the other group. So that's why we call it. You can technically read this in one format, but you have to kind of figure out, how do I realign things, right? And as I said, this encoding and decoding is not straightforward in memory. That's why we say that, okay, let's forget about this. Let's just do alignments the way that we do. And if I need something that is misaligned, I'm going to issue 2 multiple loads, okay?
Do stores have the same 32-bit semantics of loads?
Yes. Exactly. So misalignment is both for load and stores.
Yeah, another question. Does that mean that load 3, for example, is not an allowed instruction? It's like, I think byte 3, probably.
Load 3. So we typically don't do load 3. We typically just do load 0. Okay. And then we just read the bytes that we want. Actually, this is kind of variance of loads and similarly for store. So we have LW, we have LB, and we have LH. The difference between them is the second character. So LW means load word. And if you remember, I told you word means 32 bits, okay? So when I do load word, I read 4 bytes together, okay? Load byte or LB is just when we are loading 1 byte, okay? So load byte, and this is where your LB3 can work, okay? So you can actually do this. This is essentially, in reality, what happens is that we don't have load byte. What we have is we always have load word, but what we're going to do is that we're going to always just get rid of the other 3 bytes that we read. So this is 0, this is 1, this is 2, and this is 3. So when you're doing LB3, what you're really doing in hardware is that you're going to read this and you're going to discard this, okay? And this is, again, just for performance reasons, because for most of the time, 90% of the time, you want to read all 4 bytes together. Very, very rarely you want just 1 byte, okay? But for the sake of simpleness, for the sake of clarity on the software side, if I just want to read 1 byte, I can definitely do this. This is a perfectly valid instruction to use, okay? LB3, which means that I'm only reading byte 3, okay? And then finally, there's this LH. This H means half. It means that I'm reading the lower half of data, okay? So what I'm doing is basically I'm reading 0 and 1, for example, the lower 16 bits if I want to read, okay? And then this is LBU and LHU. What are these? These are unsigned version of LB and LH, because when we are reading LB and LH, since we are writing it to a 32-bit version register, since we are reading 1 byte or 2 bytes, we're still going to have the same issue with immediates, right? We have to sign extend. So these by default are sign extend things, okay? But this LBU and LHU is load byte unsigned and load half unsigned, which means that I don't care about the sign. I'm just going to read the 1 byte or 2 bytes, and I'm going to just pad it with zeros, okay? So that's the difference between LB and LBU, all right? And then for the store, we're going to have the same thing. We can store word, we can store bytes, and we can store half bytes. The only, half words, which are 2 bytes. The only difference between load and store is that for store, you don't need to be worried about sign extension because you're literally just writing into 1 byte. So it's the other way around that you have to be worried about, because you're loading smaller data to a bigger data. But for store, you're writing a bigger data to a smaller one, so you don't need to be worried about sign extension. If you don't think this is true, think about it after the class and we can again talk about it. But essentially, when you're writing to the memory, you don't need to be worried about sign extension. When you're reading from memories, then when you need to be worried about sign extension. Any other questions?
Yeah, we have a question. Oh yeah. Did you have a question? Yeah, I still have a All right, so the question is, like, when we want like a byte, we kind of like discard the bytes in like that set of 4. So how does that work in the hardware? You're
That's a
muted.
great
Yep.
question, and we're gonna discuss that when we are actually implementing this in hardware. For now, we are just focusing on kind of the structures and the contract from the software side to the system. When we are actually implementing this, we're gonna actually come back to this and say that, okay, we promised software that we're gonna do LB3. So how do we actually gonna implement this? That's an interesting question, and we're gonna get to that next week, actually. For now, just think that hardware can magically make this work. So it understands LB3, it understands that it reads 4 and needs to discard 3 out of 4, and then just gives you the one that you want. How this is implemented in hardware, we can actually exactly describe it later.
Cool. Any other questions? Yeah. I guess like when should we consider sign extension for loads?
So if you have LW, LB, and LU, these are by default sign extension, okay? If you have LBU and LHU, and then that's where you don't need sign extension. The other question is, when do I use LB versus when do I use LBU? That depends on the algorithm that you're going to use, right? So do you need sign extension for that particular algorithm you can use or not? That's a question of what software are you going to use. So that's the question of the compiler, and compiler will figure that out for you. We're going to actually have some examples in the homework, and in the discussion sessions, which you're going to kind of describe when you're going to use each of these. So yeah, in terms of hardware implementation, the first 3 need sign extension, the second 2 doesn't, right? So when we're implementing this, that's what we're going to care. In terms of when you're writing the program, you are the one as the designer, and the compiler who is kind of like translating high-level language to the assembly will understand the use case of each, and then they're going to use it properly there. Does that answer the question?
Yeah, it did.
Okay.
More question? Are the unsigned variants padded with zeros?
Yes, when we are saying unsigned, it means that we don't care about sign anymore. So we just add zeros at the beginning or end, depending on where it is, okay? And again, this is the difference between padding and sign extension. In both, you're kind of extending the size of your data to 32-bit or whatever number it has to be. Difference is, one is respecting the sign and making sure that the sign is not, been destroyed. The other one is I don't care, I just add zeros. Okay. And again, something for you to kind of review this week, either from the book or from the TAs. How does the tools complement sign extension works? That's important to know.
All right, that answered the question. Okay, anything else?
Okay. So let's,
now.
all right, cool. Thank you. So these are the 3 operands that we are using, okay? Registers, immediates, and memory. One final things before I give you a quick break is how many operands are we using? So first of all, you can mix and match these operands. So you can have an instruction that use memory and registers, or memory and and immediates, and so on. But in RISC-V, since this is a RISC-based, a simplified version, you at most can have 2 operands, okay? So you have operand, we usually call it source 1 and source 2, so S1 and S2. Sometimes you have only 1 operand for some instructions. For example, storing has 1 operand, and sometimes you have no operands at all. When we are talking about different commands, you will see that what's the difference between them, okay? So why do we have just 2 operands? Again, this is RISC-based architecture. We want to keep everything kind of hard-coded and constant, and that's why we just do 2. In more, complex-based CISC version of ISAs, you might have multiple operands in one instruction, okay? So just something to keep in mind. All right, so the second thing is the command. Let's have a quick break of maybe like 5 minutes. It's 10:02 here in Eastern, European time zone. I think it's 1:12 there. So let's come back maybe at 1:16, 1:17. Okay. recording. Awesome. Okay. So let's continue. So we kind of figure out the operands. Of course, we're going to do lots of, examples in the homework and in the discussion sessions to kind of figure things out. But let's also talk about the commands, and then now we will have the full picture, and then we're gonna actually have some real examples. Again, want to emphasize that everything is 32 bits, which means everything is fixed. So the combination of commands and operands should be 32-bit. So what are these commands? What are these instruction types? There are three groups, okay? There is arithmetic, or generally we call them ALU operations. There are memory-based operations, and there are control flow operations, okay? So similar to the operands, let's break each one down. So the arithmetic one is the most common one. It's the one that's, probably it's the simplest one as well. But it's kind of like the majority of operations that we do is ALU operations, okay? And as the name suggests, we are doing some arithmetic. By the way, ALU means arithmetic logic unit, or generally just our arithmetic operation unit. So we do two types of arithmetics, okay? We either do an arithmetic on two registers, okay? So we kind of like add register 1 to register 2, subtract this and that, and so on and so forth. I'm going to actually give you a list of different arithmetics that we're gonna focus in this course. Or we can do one register and one immediate, okay? Of course, two immediates doesn't make any sense, right? Because if I want to kind of subtract 5 and 10, I will just do -5 to begin with, right? So two operands as immediates doesn't make any sense. So you just do one register, one immediates, or two immediates. And important things about ALU operations and other operations is that you want to also store the results somewhere, right? So for example, you add two numbers and then what, right? So you have to store it somewhere. That somewhere is usually another register, okay? We typically don't store things directly into the memory. We typically just store them into the register because we want fast operations in ALU, okay? So we call them this other register, we call this destination register, okay? So these are the source registers, and this is the destination register, so where we store things, okay? So as I said, source and destination. So let's focus on two registers examples. One instruction that's very commonly used is sub. So it's sub x3, x2, and x1. Or we have something like add x5, x1, and 10. So this one is register immediate. This one is register, okay? So the format that we are using is when we are listing it like this, the three different, the leftmost one is always the destination, okay? And this one is usually source 1 and source 2, okay? So typically this is source 1, this is the source 2. I might be mistaken, but I think this is source 1 or source 2. It generally doesn't matter that much. But what is important is the leftmost one is the destination register. So what does this do is essentially means that x3 is equal to x2 minus x1, okay? So this is this destination register. This is where we're going to store things. And this is the source register 1, source register 2. This one says that x5 should be equal to x1 plus 10. Okay. So for example, if this one had been minus 10, then this would have been x5, x1 minus 10. Okay. So essentially it's kind of a sub. All right. And by the way, this is a mistake here. This should have been add I and not add, okay? Because this is an immediate, so it should be add I, not add. The difference between add and add I is add I has an immediate, okay? So this is a typo that unfortunately I forgot to fix, okay? So destination on the left, source 1 and source 2 on the right. This is the list of instructions that we care about. This is the base RV32I, the base implementation of RISC-V. As you can see, there are lots of arithmetic operations. So let's actually go one by one. So as you see here, this is the kind of the command in the first column. The second column is actually the syntax that we are using, okay? So add I, RD is the destination register, RS1 is source one, and the constant is the immediate number. For example, but for add, what we have is that add RD, RS1, and RS2. So the difference between add and add-I is the RS2 here is the register versus in the immediate format is an immediate. The third column is basically just description of what this does. So for example, this is add immediate versus this one is add. And this is basically just the mathematical operation that is what's really happening. So think about register file as this array. So reg rs1 means that, for example, if rs1 is x3, this means that we are reading x3, we are adding it with some constant or immediate, we're storing the results into the register RD, okay? So think about reg as a 2D array, which each row is the register number, and within that, there's a number that we are storing, okay? So let's go one by one. So I already talked about add and add-I. You see the difference between them. Let's talk about the others. As you can see, add and add-I is not the only ones that we have. We have also a bunch of others. So we have XOR I and XOR. We have OR I and OR. We have AND I and we have sub. Notice that we don't have sub-I because sub-I and add-I is basically the same thing, right? So add-I with a negative number is as if that we are doing sub-I with a positive number, right? So this is the same thing. But generally, these are all like very basic arithmetic operations. If you don't remember, for example, what XOR was or what OR was, again, it's a good time to go back and kind of brush up on your digital logic course. But these are just basic logic operations, okay? And then you can always like take a look at what is happening here. Then we have this other two things called SRL and SRA. These are shift operations. So we have shift right and we have shift right. The difference between these two is shift right logical versus shift right arithmetic. The difference between these two is that the logical one, when we are shifting things to the right, okay, so if I have a number here and shifting it to the right, I'll move things to the right and then I'll have empty spaces here. And if you remember, if this is a sign value, this is the sign bit. So if I shift things to the right, now the question is, what should I do with the sign, okay? If this is shift right logical, it means that I don't care about the sign. I'm going to just padding it with 0. Okay, if this is shift right arithmetic, it means that I do care about the sign, so I need to sign extend this when I'm shifting it, okay? And the way it works is that, as you can see, SRL and SRA, it has the destination register and source 1 register and source 2 register. What happens is it basically says that I need to shift register 1 by the amount of register 2, okay? So for example, let me give you an example. SRL X3, X2, and X1, okay? What this means is that whatever value is stored in X2, read X1, whatever value is stored in X1, shift X2 by that amount and store it in X3, okay? This is basically what this says. So for example, let's see, give you another example. Let's say X2 is stored, the value stored in X2 is 8. Let's say the value stored in X1 is 1. So what happens is that this one says that shift 8 by 1 bit, okay? This will be equal to 4, and I'm going to store 4 in X3. That's really what is happening here, okay? I'm shifting 8 by 1 bit to the right, which means that's going to be 4, and now I'm going to store 4 into the register destination, which in this case, X3, okay? And as you can see, there's like a tiny bit of like kind of hint here to kind of help you to distinguish between SRA and SRL. This S thing says this is signed shift to the right, versus this U says this is an unsigned shift to the right, okay? We also have SLL, the shift left logical. One thing to notice is that there is no shift left arithmetic because there's no difference between arithmetic and logical when you're shifting things to the left. Okay, because when we are shifting things to the left, there's no need for sign extension because it's on the LSB side. And in LSB, you always add zeros. There is no option of sign extension on the least significant bit. Again, if it doesn't make sense, you probably want to think about the logic design one more time. Okay, so we have shift left logical, which is exactly similar to the way that SRL and SRA works. We also have the immediate version of this. Okay, so difference between these guys and these guys is that in this one's the RS2 is a register, versus in this immediate versions the RS2 is the constant. So for example, SRAI is x3, x2, and some number, so like 2, which means that I'm going to shift right arithmetic to the right by 2 bits. So I'm going to kind of divide it by 4. Okay, versus this one was something like x3, x2, and like something like x1. Okay, so this is SRA, which means that the whatever value is stored inside x1, that's the value that I'm going to use to shift things. Okay, same story with SRLI and SRAI, and the immediate the immediate counterparts of the regular ones. We also have this SLT. This SLT means set if less than. Essentially, what it does is it checks these two registers. Let me use a different color. So you're going to compare this to if RS1 is less than RS2. So set less than. If RS1 is less than RS2, then it's going to set this register. It means that it's going to write value 1 into the destination register. Okay, so it's just a comparison. Okay, we're going to use this a lot for our comparisons in this class, and then everything is signed. Okay, SLT is signed set less than. If we have SLTU is just comparing the absolute values of register 1 and register 2, so it doesn't care about sign. Okay, so just comparing the absolute values, and again it's going to set the destination register if RS1 is less than RS2. Okay, so this is SLT and SLTU. Again, the difference is just the way that we compare. The first one we compare it sign wise. The second one we're just comparing the values and not the signs. We also have the immediate version of the same thing. Essentially, what it does is compare RS1 with the immediate and not the other register. Again, you can see the actual mathematical operation here as well. All right, I guess that's it for all the integer or arithmetic instructions. Any questions here?
All right, I think we're good.
Cool. I guess you can always go back into this table and think about it and let us know. Your first project would be implementing this in C and then creating an actual processor that kind of decode this. So you're going to actually come back to this table a lot when we are actually doing the project. But feel free to ask questions either here or on CampusWire if you don't know exactly how each of these instructions works. But this table is pretty clear. You can always come back to this table. Okay. So for example, I'll give you an example. What is the final value of x3? So let's actually go together. So this first instruction is add I x1, x0, 3. Remember that this is the destination register. Basically what this does is storing x3, x0 plus 3 to x1. If you remember, I told you x0 is always hardwired to 0. So it means that at this point, x1 is equal to 3. Then we're going to do another add-I, this time x0 and 5 to x2. So this means that x2 will be equal to 5. Then we're going to add x2 and x1 and write the results to x3, which means that we are adding 5 and 3 and write the results to x3. So x3 will be equal to 8. And then we're going to do SRA, shift right arithmetic. So what this does is saying that whatever value is stored in x3, shifted to the right by the value that's stored in x1. Okay, so x3 is 8 x1 is 3. So it means that I'm shifting 3 bits to the right. So it's going to be equal to 0 if I shift it by 3 or no. Right? So this is 1, 2, and 3. Sorry, it would be equal to 1. So x3 would be now equal to 1. Okay? So that's kind of the idea that we're going to use for this. So the final value of x3 is 1. One thing to notice is that you can use the same register both for the destination and source because these are sequential, which means that I'm going to read the old value of x3, do some operations on that, and then I'm going to store the results into the destination, which happens to be, again, x3. So this is kind of like something that we have in C as well. So we have something like x is equal to x plus 1, right? Like we very commonly use this, which means that this is the old value added by 1 and stored on x. This is exactly the same thing as happening here, okay? So we can always like try this and some other mini examples. I'm gonna let you guys to do this yourself. So the idea here is that, let's say we want to create the sum of this value. So I want to add 0, 1, 6, 8, and 9. And then I want to left shift it by 2 bits and then subtract it by the 2 bits version of itself, okay? It's kind of like this. So I first want to sum this and write it to y. Then I want to left shift it, right shift it, and then subtract them and then write it to z. Can you write an assembly code for this? Okay. I'm going to give you like 2-3 minutes. I'm not going to, give you the results for here. In the discussion sessions, maybe the TAs can give you an elaborate version of this, or I can just post it on CampusWire. But let's have it like a 2-3 minutes for you guys to think about this and see if you can write it down yourself, and then we can continue. Okay. I'm gonna actually put it here for you guys. Might be easier. Sum of 1, 6, 8, 9 to y, and then z is y. Was it left shifted or right shifted? Yeah, left shifted by 2 minus y right shifted by 2. And you can use this table basically to kind of write your instructions. Let's have 2 more minutes and then we're going to continue. All right, for the interest of time, let's continue, but try to finish this and then we're going to discuss it in the discussion sessions, or I'm going to, if somebody can just post the answer on CampusWire, that would be a great thing to do. You're also going to get some points, right? So whoever solves this, just post it on CampusWire. All right, so that's the first thing. This is the most common type of activities that we do, and that is arithmetic or ALU operations. Let's quickly go over the other two. We're probably not going to finish it, but we'll probably cover memory, and then next session on Thursday, we're going to talk about the other. Okay. So memory, I already talked about load and store. This is essentially the only two operation that we need for memory. So I talked about the addressing mode that said that we're going to use base, register, and offset, right? So the base is going to be of the register. The offset is basically the immediate. There are other ways of addressing, but RISC-V doesn't use those. So we just use base plus offset, okay? And I already talked to you about the word and half word and byte. So LW, LH, and LB. I also said that there is unsigned version of LH, which we call LHU, and there's the unsigned version of LB, which is LBU. Of course, there's no unsigned version of load word because load word is already 32-bit, so there's no such a thing. And for store, we have a store word, we have store half, and we have store byte. And none of these require sign extension because we are writing a bigger number to a smaller number. So this is kind of the syntax. Similar to the table that I showed you for arithmetic, we have all these things here. You see LB, LH, LW, LBU, LHU, SP, SH, and SW. So the syntax is important to think about and to look at. So RD is the destination, okay? And remember, for these load instructions, destination is what we read from the memory, okay? So whatever we read from this address, basically, if you look at here, we have the address, okay? We read the memory from this address, we sign extend it, and we save it into the register file, okay? That's what we do with LB, LH, LW, LBU, and LHU. The only difference is, as you can see, what we read is slightly different, right? So essentially, load word, we are really reading 4 things together. We kind of concatenate 4 bytes together, versus for load bytes, we just read that one particular address. How do we calculate the address? We calculate it this way. So this is our base, this is our offset. Also pay attention to the syntax that we are using here. So for example, we are using LB, X3, 10, and X0. What this means is that this is our base and this is the offset. So we put the offset outside the parentheses, okay? So what this means is that just add RS1 to offset and that is your address, okay? So your address is this. And then as you can see, there is a difference between sign extension and zero extension, and then this one doesn't need sign extension. Then we have stores. The difference between load and store is that in store you write to the memory, right? So in this case, there's one thing that people always confuse, and in store you don't have destination, okay? The destination store is your memory. So everything you have is actually, all of them are source. What are the difference between RS1 and RS2? The difference is in store, you use RS1 for the address. For calculating the address, you use RS1. And for the data that you want to write to the memory, you use RS2. So basically what happens here is that, as you can see, for example, in store word, we have store word, RS2, offset, RS1. So for example, we have store word, X2, 10, X0. What does this mean is that I'm going to calculate the address this way. I'm going to use this RS1 as X0 plus 10. In this case, it would be 10. This is my address. What value I'm going to store into this address 10 is this value of RS2. So reg RS2 should be written into the memory address to address plus 3 because I'm writing 4 bytes altogether. If I do address stored bytes, I'm going to use the lower 8 bits of RS2. Remember, we are writing just 1 byte, and we always just pick the first byte of the register. And then we're going to write it into the address that is calculated by RS1 plus offset, okay? So don't be confused by this. There's a difference between RD and RS. They look exactly the same, but this one is RS1 and RD, this one is RS1 and RS2. People always confuse these two together, so be careful, okay? All right, the last thing I want to talk about, and this is just, I'm going to give you like the brief overview and then I'm going to let you guys go and then we're going to talk about it next time. And that is the control flow. So what is a control flow before actually talking about this? Remember I told you that we're going to use store program order, right? So we have memory, we have CPU, we have this special register inside the CPU called PC, which is essentially what it does is just pointing to a particular address in the memory. And what it does is it's going to fetch this address, this instruction, execute this, and then go to the next one and next one and next one, okay? We call this control flow because essentially where we start, when we go next, and we read these things one by one, okay? So this is what we store in this PC program counter register, okay? So you might think that, okay, all we need to do is just doing things linearly, right? So we store from, let's say, address 0 and then 1 and then 2 and so on and so forth. So why do we need to even keep track of this? The reason for this is that if you think about if then else's in your programs, okay? So if means that, there's a condition. If condition is true, you have to do something. If the condition is not true, you have to do something else, okay? So think about this in the linear format. What you would do is that you're running a bunch of instruction. This is your, for example, if instruction. And then if it's true, then you might execute these instructions. But if this condition is not true, you don't need to run this. You have to kind of jump over them and maybe run this else instructions, okay? So in a linear memory, if you have if then else's, if you have this, different branches, you need to be able to change your PC and jumping different places, right? Same story for case and switch, same story for your while loops and for loops. All these things is checking some condition. Based on that condition, decides to do something. So in that case, I need to change my PC in order to be able to run these things, okay? So my PC, for example, is pointing here, but if the condition is true, maybe it has to jump somewhere else. So I need the capability of checking the condition. I also need the capability of changing the PC. So these are the instructions that we need to have, okay? So we have two types of kind of instructions, the jump instructions and the conditional instructions, okay? Why do we need this? Because of these kind of things that I said, because all these conditions that we have, if then else's, while loops, for loops, and so on and so forth. We also have lots of function calls and returns, right? So we are in the main function, and then like some other function like we call foo, we jump into the foo, we run it, at some point we have to return, we will return back to here and execute this, right? So you keep changing back and forth in different parts of the memory, right? As a result, I need to be able to change my PC, okay? So this is what we call the control flow here. So as I said, there are two things that we need to implement. There is jump instructions and there are branch instructions, okay? The difference between jump and branch is jump is unconditional. We always jump. We don't care whether this particular condition is true or not. So why, for example, we need jump? For example, in the main function example, when we get to the foo, you never check whether something is true to call the function, right? You always just call it. So in this case, I just need to implement what we call a jump. But if, for example, we have something like in the main function, if some condition, then do, for example, call foo. In this case, it's not just a jump, it's also a branch because I need to check whether this is true or not. Based on that, do this. Otherwise, I need to skip this and do something else, okay? So there's a difference between jumping and branching, okay? For both of them, you need an important thing, and that is the destination address, right? So essentially where to jump, right? And if you remember, I told you that all of our address are always base plus offset, okay? So we always do base plus offset. And for control flow related, especially for jumps, our base is usually PC, okay? We already have access to the PC. All we need is the offset, okay? So we don't really say that, okay, jump into this exact memory stage. We always say jump to this PC plus 4 or 8 or something. So we always do what we call PC relative jumping, okay? And then one last thing before I let you go is that there's this branch instructions, which is also changed the PC. The only difference is that jump always change the PC versus branch sometimes change the PC, sometimes doesn't change the PC. The difference is if the condition is true, we're going to jump. If the condition is not true, we're not going to do anything. So branch is basically do nothing if the condition is not true. Okay. So that's where we're going to stop. Next time I'm going to talk about jump and linking and branching, and then we're going to talk about how do we implement this in our system. If there are any questions, I'm going to stick around a little bit more on the Zoom. So you can maybe just come to the front of the class and ask your questions. Otherwise, I see you guys on Thursday.